Okay, let's get started. So today, we're going to talk about modulation, which is used in communication systems. And there's all kinds of modulation schemes, but we're really going to talk about just multiplying a cosine times some frequency data. But before we get to that, we need to get some definitions. And so the first one is, what do we mean by bandwidth? All right. Now, what this is, you could say, is that we have taken the Fourier transform of a signal, right? So this axis is frequency, right? And so this is the actual signal components, as opposed to the Bode plot, where we're not necessarily seeing the signal, we're looking at the system. Now the thing is the axis is frequency or radians in either case, but if you look at the complex plane, right, this is j omega minus j omega, and this is the real part. Now in the S plane, right, you can have a pole, you can have a zero, that's where your HS is. But in Fourier, basically you are really only along this omega axis, because everything is a cosine, right? Fourier expansion, you can take any periodic signal and turn it into a sum of sines and cosines, right? And if a signal isn't periodic, like let's say this lecture, well, just repeat it. You know, like if this lecture was on repeat, well, then the whole lecture would be periodic, right? So what this represents is, you know, it could be a song or any kind of thing in time where you've taken the Fourier expansion, and so all the frequency components are in here. And I don't know if you remember, but a lot of, well, it's true when we're taking the mathematical of like some well-defined signal, you get this spectrum. When you look at that Fourier, the FFT, right, if it's not perfectly sampled, right, things smudge out. So that's why you don't see a sum of spectra. It's all merged, right? And that shape is just some kind of random thing. So this starts off at DC and goes to F max, right? And we get the and in this case, we also need the negative side. So the Bode plot is calculated by changing j omega, right? Or, you know, j 2 pi f, but we just use the positive axis because that's log, right? If I were to do a low pass filter, right, plus j omega minus j omega, you would see this symmetric shape, something maybe a little more symmetric. Now, yeah, we don't put j omega or 2 pi f j because you know that it's a sine wave. You just drop that out. All right. So this is the bandwidth of the signal, where before we might have talking about the bandwidth of a filter, right? So basically, if your ears are pretty good, you can hear from 20 hertz to 20 kilohertz, right? And human speech is from 80 to 14, all right? So we don't actually hear DC okay. So in human speech, right, that could be 20 hertz and that could be 14 kilohertz. All right. And so our ears are a bandpass filter. All right. So just to summarize again, this is the signal that we wish to transmit, right? And it has a bandwidth, right? You know, music and things like that doesn't have a DC component. So really, this is what we have. And the shape is arbitrary, right? It could be, that's just the sum of the signal. It could be whatever you want it to be. Maybe not that. So what we're going to do is modulate it. All right. And so we take a signal, xt, right? Sum of sines and cosines, or cosines with a phase, right? And that you have the magnitude. All right. So we can convert anything into that. We are going to multiply it by a cosine. FC carrier frequency, right? So Carrier frequencies, you might right, for AM it's in the kilohertz, right? And you can have 750 kilohertz, 760, 770, 780, right? FM, we use higher frequency, right? But those are the frequencies that we're going to transmit at. And right, the frequency of the carrier has got to be a lot bigger than the maximum frequency of the signal. All right. Well, to actually see what's going on, we need to take the Fourier transform, but multiply here is convolution in the frequency domain. So let's just say okay. So now we're going to convolve these two signals. Now, while convolution is difficult, convolution of a delta function is not that difficult. And so this delta function, right, if you convolved in the time domain dt minus 1 xt, right, you convolve those together, you would get x at t minus 1. Well, it's the same thing in the frequency domain. Right, 0, positive frequency, negative frequency. We just do delta function. So this is negative FC, positive FC. Okay, we have two delta functions. And then this XF, I'm going to try to draw this symmetrical. All right, it's not perfect. Minus FM for frequency max. This is supposed to be centered around 0. Well, when you convolve this with these, everything is translated to plus or minus the carrier frequency. And so this is used kind of again and again, where to demodulate, you actually multiply it by the same thing again. Now, so the symbol of a modulator, right? Is an X, right? Because we're doing a multiply. Now the thing is there's all manner of ways to multiply. That even if it's not a perfect multiplier, it'll still work. But the specifics of that I'm not going to go into. All right. Now that's basically one kind of modulation, right? FM modulation is you have a carrier, right, that you have a base carrier frequency, you have a voltage controlled oscillator, this is XT, and you're slightly changing the I'm making it look like amplitude modulation, sorry. Basic, hey son, sorry, teaching here. You know, there's one frequency, and then I'm trying to make it faster, right? But it's still centered around a carrier frequency. Basically, that is just being the frequency is just being modified by XT. Then there's even phase, right, where X of T can modulate the phase. All right. But for the purposes of the homework, really, we can just talk about the modulator being a multiplier. How it's done, you don't really have to say. But from analog devices, they have the 833, the 633. You can buy one. That's a whole research area in and of itself. All right. So, you know, how does a transceiver work, right? You have the sound, you know, converts pressure to voltage of time. So converts pressure in time to voltage in time, right? This frequency is whatever the carrier frequency is of your radio station. You multiply these together, right? And you get this. All right. Now, the phase you really wouldn't have this spread. You would still have your delta functions. And the fact that the phase were changing, because this is only magnitude, you'd need another plot to show that the magnitude, that the phase was changing. Here, what it is that delta function of whatever frequency you're at is moving back and forth depending on whatever xt is. All right. So and then that goes into the antenna. So that's the first part, transmission. Now for receiving, right? So the thing is right, all radio signals are present at all times. That's why it's so great, is that all the radio stations are transmitting at the same time. You just have to tune into one particular one. So there's all these other radio stations, right? This one happens to be NPR, right? So the channels have to be separated by a certain distance, right? And that's why I think you can only tune in terms of half, right? Because they're spread out. So the thing is, all these are there, and I want to get rid of everything except these. Well, RF is radio frequency, right? And we need a bandpass. And a simple bandpass is just, an LC circuit, right? So the antenna will come in and you can tune the capacitor or tune the inductor to get a rough idea to move that bandpass around. So if I wanted 98.5, right? I'd want to move my filter from here. I need to move the filter from here to here. Okay. So that means I could just tune the resonant frequency with one of these. All right. Now the signal comes out pretty small, and so you need an RF amplifier to make it bigger. All right. Now, so now we kind of do a rough bandpass filter. We amplify it, right? So we're still got our original carrier frequency. What it is we don't have the others. We've gotten rid of everything else. And we put it through another mixer. And the thing is that the bandpass frequency here and the frequency here always make this. So what they call it is heterodyning, meaning when you multiply a cosine by a signal, you get other frequencies. That's all. That's really all heterodyning is. But rather than before, where you multiplied it by the exact frequency that you had before, you're tuning it so that what comes out of here, right, is an intermediate frequency. Okay. Now, before, right, in order to capture whatever channel I wanted, I had to tune this, right? And this RF amplifier has to amplify over any of these frequencies. It's got to work for the whole spectrum of the radio stations that I'm at. But what we do in this case is we mix it so that the local oscillator is a function of the bandpass, so that we always get the same intermediate frequency. Okay, so it's not, so as you control the knob, you're controlling this and you're controlling that. And then because there's like a lot of leakage, it's not, this isn't a perfect bandpass. You got to bandpass this part again, right? And now you've got the actual, you've actually put it on a different carrier frequency. Which again, you have to amplify. And then there's something called the demodulator. All right. Which is it's a half-wave rectifier. All right. And so what happens is, as the signal is changing, like I'm kind of bouncing, right? This is the signal, and I'm trying to show that it's all at the same frequency, and it's just going off and on, right? The diode only allows it through, right? And then this RC filter makes it so it can't discharge. And so you'd get something like that. Oh yeah, you could use a full wave rectifier for that as well. Now the demodulation for FM and phase modulation is different. But this is, and the thing is you could make a diode right out of a pencil and a paper clip, which is kind of why AM is great, is that you could be in an emergency and you could always kind of make an easy radio. Of course, everything is digitized, or anyway, but FM, so the thing is AM, it's easy to modulate and demodulate, but it really does have its issues. Frequency modulation, you can get a lot more data. It's a lot cleaner, less prone to problems. But so basically that's, you know, how does a radio work? You've got to take your original data, multiply it by a cosine, you get positive and negative, and you convolve that. So now you've converted your data to a higher frequency, right? And then you got to transmit it. And then really you need an antenna to get it, a bandpass to filter out all the other signals, right? An amplifier, and then another and another multiplier. Now, the old way of doing it is the multiplier, it's just a random local oscillator that you tune just to the frequency in question. A separate heterodyne is such that it's a local oscillator so that when you multiply it together, you get the same intermediate frequency no matter what. That means this part never has to change, right? I can design these components and they never change. And then I just need a tuner here and this here. That multiplier would be the same, RF amplifier the same. So it makes it a lot cheaper. If you did it the other way, you'd have to tune everything for every channel. And if you look at it, Wikipedia has a good introduction. That's what they had to do. Like, you needed 3 knobs and practically a PhD just to turn your radio on. All right. So as far as the homework is concerned, yeah, I want you to put that into your own words, and the more that you can show how the Fourier transform is being used and how its convolution in the frequency domain comes from multiplication in the time domain, all right? And now you don't have to do the separate super heterodyne demodulation. You can use the simpler one in the book. You don't really have to show any circuits if you don't feel like it, but in this case you have a band and a band in the what you might call double sideband. What actually happens is this if this local oscillator is the same frequency as the carrier, then you can get away with a low pass filter. All right. Any questions? Okay. So let's talk a little bit about bandwidth again. And what this is that this is an electrical signal coming out of a sensor that's measuring basically you have your finger, right? And you have blood going through your finger. Okay. And it's when it's beating, it puts a pressure on everything and your index of refraction changes. You know, it could go up, and when it's after the beat, the index of refraction goes down, and you are sending infrared light through to a sensor, and that change of index of refraction is modulating that infrared light. So in fact, that's another modulation scheme, right? Where if I have light, right, and I have a material with an index of refraction, and I have a pressure in T, right? I'm getting a light signal that's modulated, and then I have a diode detector, which then modulates the current. Anyway, so this is almost like a radio, an optical radio. So what you get is like a triangle wave with a whole lot of noise on it. And you'd want to know what is, so if I needed to design a filter to get like the part of the signal that I want, really the best thing to do is to take the FFT, right? And so, yeah, I have 1 hertz because when I took my pulse, I was relatively relaxed. So, 60 beats a minute or 1 beat per second. But then, yeah, I've got other frequencies due to the fact that if I take the spectrum of a square wave, I'm going to have all these here, and then the noise, right? So in fact, what's the bandwidth? Well, it goes from 1 hertz really to 100 hertz. So that's actually my bandwidth, right? In today's example, we would have shown the negative frequencies as well. But then if I really just want my heart rate, right, I need a band pass around the 1 hertz. Okay. Oh yeah, it might have been, that's just how this signal works. But yeah, if it would do a square wave, that next heart, I'd have a 1 hertz harmonic and then a 3 hertz, 1 hertz fundamental, give or take, and then it would skip to 3, if I could even get it 50%. But this is a reverse triangle wave, and so you have omega 1, omega 2. They're all present. Okay. I just wanted to double check. All right, but the exam is next Wednesday, starts at 12:15. AEC accommodations, I'll start it here, and I can read off what's going on and just create create your time slots. All right. I'm gonna have to go with different versions, but for like there's, and what I mean by that is different versions for everybody. All right. So that there'd be like 4. All right. But otherwise the same format, except taking attendance was it didn't really seem to do what I wanted, and it was a pain. So we won't take attendance. But yeah, have your Zoom on just so I can see that you're okay. It's open book, open note. Open resource, just not open person. All right. I didn't really see any. I couldn't detect it. Oh, I see your chat. Just let me finish my thought. I couldn't detect any cheating. Um, and it's just basically things are stressful enough without some kind of recording thing. Yeah, I'm sorry. I shouldn't laugh. Yeah, of course, calculators are allowed. They're always be allowed, right? Um, the thing is again, the honor code is still in effect. We'll have different versions of the exam. Um, and what really seemed to happen is you really have to prepare for an open book, open note exam differently because you can't assume you're going to be able to look anything up quick enough. You really have to, you almost have to know it better. And then you only look up an equation or approach just to verify that you're in the right direction. Now, I'm not going to create, I create brand new questions each time, but I'm not going to radically alter the kind of question. Um, for instance, maybe not that you need to know, but next semester, yeah, we're supposed to be online, and it could be no, design a DF2, and everybody gets a different filter spec, and that you actually do it and submit the LT Spice file, right, along with your work. That's just I think that's too much of a shock to all our systems to um, go through that this semester. All right. So what I've done is I've created another in-class thing. I will break everybody up into groups of, or attempt groups of 3, right? Um, the question is a review off of midterm 2, and the questions are all similar, but the resistor values used will probably be different for everybody. But unlike maybe some others where, yeah, everybody was extracting a second order low pass, except was it over, under, or critical, and everybody had a different, it's pretty much all the same problem that I guess we'll just let you see. So let's see. Now, something happens when I start going in and out of rooms that I accidentally go on mute. So if you think I should be talking, I have no problem with you telling me that I have made a mistake. So it's activity 28. All rooms are now open. All right, guys. You should join your room. Angel, Edward, Emmanuel, Angel, Edward, Emmanuel. Let me know if you don't know how to do it. That just let me know. I'll figure it out. Hey Ed, how's it going? Hey Ed.
Oh no. Oh, for 118.
No, for materials.
Oh, for
112.
materials.
He's materials is either gonna do Proctor U or whatchamacallit? Proctor U or the Respondus lockdown.
Hey guys.
Hello.
Nice RuneScape, Miguel.
Yeah.
I did the question already.
Yeah. No. I'm not trying to spy on you. But maybe if everybody didn't do the question, you could. Oh, you know what?